Welcome to ECO 5347, Advanced Econometric Theory. For this course, we're going to be using the textbook A Guide to Modern Econometrics by Marno Verbeek. The reason why I've chosen this book is it bridges the gap between a typical undergraduate econometrics text, which is written in scalar mathematics, and heavy-duty, industrial-grade PhD level texts which are written in matrix math. This text does an excellent job of showing both methods. It's written primarily in matrix math. The reason why we use matrix math is because of simplicity and ease. Matrix math or linear algebra is one of the prerequisites for this course, but we begin in section 2.1, where Verbeek shows us typical ordinary least squares regression and asks us to somewhat paradoxically think about it as nothing more than an algebraic tool. And I will use this as an opportunity to show the equivalence between the scalar math techniques that you are familiar with from undergraduate econometrics and the matrix-based techniques that we're going to be using for the rest of the course. So with that, we will begin considering regression as nothing more than a linear approximation of some variable y sub I. So we have a value y that we're going to, in essence, draw a tangency, right? Think of this as a two-dimensional graph with y on the vertical axis, x on the horizontal axis, and we're going to use the value of x to make a linear approximation of y. More variables certainly do give a better approximation, but the virtue of using one variable is mathematical simplicity and the ability to draw pictures. We can graph this linear approximation. This is a very typical graph showing the use of x to approximate y. In this graph, each of the dots represents the plot of the value of x and the value of y for that particular observation within the data set. And the linear approximation is given by the equation here labeled SRF, the sample regression function. The notation used in this graph is just a little bit different. If memory serves correctly, I stole this from Gujarati's text. But we have the approximation, the linear approximation of y given x sub I as given by the regression line. So for instance, for this first value, x sub 1, what you will notice is that we have the actual value given rather high, and then the linear approximation is given by the regression line. The vertical distance between the regression line and the actual observation of y is the error term. Now, Gujarati denotes this as u sub I, but Verbeek, we're going to find on the next slide, denotes it as e sub I. Okay. So let the regression residual or the error term be the difference between the actual observation and its linear approximation, and we're going to define the ith error term or ith regression residual as the actual value y minus its linear approximation. Now, when we choose the parameters beta tilde 1 and beta tilde 2 to come up with the optimal linear approximation, of course, it's not possible to minimize the sum of the errors over all observations in the data set because positive and negative errors will cancel out. So the sum of the e sub i's are going to equal 0. I'm going to show a mathematical proof of that a couple slides into the future, but for now, think of the intuition of why positive errors and negative errors will cancel out. So if the regression line goes through the central tendency of the data set given by X bar and Y bar, then positive and negative errors numerically cancel out for all values of beta tilde 1 and beta tilde 2. You remember from the prerequisite course that what we do instead is we choose beta tilde 1 and beta tilde 2 to minimize the sum of the squared residuals. And the virtue, of course, of squaring the residuals is that the square of a negative residual is positive. So we get a sum of positive terms. We choose beta tilde 1 and beta tilde 2 to minimize it. The vice of minimizing the sum of the squared residuals, you recall again from the prerequisite course, is that large error terms or outliers can have an inordinately large effect on the values of beta 1 and beta tilde 1 and beta tilde 2. We're going to cover that in the future. But for now, remember, we're thinking about regression as an algebraic tool and nothing more. And what we're going to do is we're going to choose beta tilde 1 and beta tilde 2 to minimize the sum of the squared residuals. So if we are going to do that, what we of course will do is we will differentiate the sum of the squared residuals with respect to beta tilde 1 and with respect to beta tilde 2. If I take the partial derivative, you remember a partial derivative means I'm differentiating this expression with respect to beta tilde 1, holding everything else constant. So I'm treating beta tilde 2 as if it were a numeric constant when I'm taking the partial derivative with respect to beta tilde 1. I take the derivative with respect to beta tilde 1. You will notice that in this expression, the expression of the sum of the squared residuals, beta tilde 1 appears in one place. So when I apply the product rule, what I do is I take the squared term, move it out front, and then take then decrement the exponent, and then I take the derivative of the inner term with respect to beta tilde 1, and I get the expression that's on the second line. You will notice that the first expression in parentheses, yi minus beta tilde 1 minus beta tilde 2 x sub I, is actually our definition of the regression residual. And if I eliminate the negative sign and the scalar multiple of 2, what I have then is that when I differentiate the sum of the squared residuals with respect to beta tilde 1, this gives me the very important result that the sum of the regression residuals must equal 0. We talked about intuitively why that should be so a couple minutes back, but here what we find is that by construction, the sum of the regression residuals must be equal to 0. Okay. Then, when we differentiate the sum of the squared residuals with respect to beta tilde 2, we get this second expression. The sum of xi e sub I is equal to 0. These two equations, the sum of the residuals is equal to 0, and the sum of each residual multiplied by the explanatory variable x is also equal to 0. These are called the OLS normal equations, right? They're true by construction, by the definition of how we define the ordinary least squares estimators. If I take the two OLS normal equations and manipulate them, I can solve for the values of the OLS the OLS slope and the OLS intercept. So if I take the first equation, remember the first equation was that the sum of the error terms or regression residuals is equal to 0. As I manipulate that, going from the first equation to the second, what I'm doing is I'm breaking the first set of parentheses. So I get the sum of the dependent variables, y sub I, and then I'm adding up beta tilde 1 n times. So if I add a constant to itself n times, the result is n times beta tilde 1. And then the final term, because beta tilde 2 is constant with respect to the index value I, what that means then is that beta tilde 2 can come outside the summation term. So I get that second line. And then moving the n beta tilde 1 to the left-hand side of the equality, I get the third line. And you can see from here it's quite easy. What I do is I divide both sides by the sample, the number of observations n, and I get an expression for beta tilde 1. Now, 1 over the sample size times the sum of the y sub i's is very clearly the mean of y. So what we can say then is that the OLS intercept term, which Verbeek denotes with b sub 1, so Arabic b. Oh, I might add at this point that in Verbeek, anything that's a Greek letter is an unknown, unobserved value, and the Latin analog, right, so is our estimate of it. So what we can say then is beta tilde 1 is an unknown value, right? It doesn't have a statistical distribution. It is a discrete value. Our estimate of it is b sub 1, where b is the Latin analog to the Greek letter beta. So b sub 1, which is the OLS intercept, is equal to y bar, the mean of y, minus b2 times x bar. Now, manipulating the second equation will allow me to solve for b2, the OLS slope. So we start with the equation that we're going to manipulate, and then I'm going to do something that's that may seem perhaps a bit odd, but you'll find that a lot of econometric proofs do things such as this. What I'm going to do is I'm going to add this second term, x bar sum e sub I. I can add that to the original equation because the sum of the regression residuals is 0. You remember that this is true because of the OLS normal equations. I'm going to show you in a moment a mathematical proof of it. But remember, we have multiple ways of showing that the sum of the OLS residuals is equal to 0. So adding that piece in, what I can do then is, moving from the second line to the third line, I'm moving this entire expression under one summation, right? So I can do that by bringing the x bar sum e sub i's under the same summation as the first term. And then going from the third line to the fourth line, what I'm doing is I am inserting the definition of the regression residual. Y sub I minus beta tilde 1 minus beta tilde 2 x sub I. And then moving from the fourth line to the fifth line, I'm inserting the definition of the OLS intercept that we just derived from the previous slide. It's y bar minus b2 x bar. Okay. So combining like terms for b2, I have now this next equation. And moving b2 to the left-hand side of the equality, now it's abundantly clear how I would solve for the OLS slope. I would divide both sides by the sum of xi minus x bar quantity squared, and I get the familiar OLS slope. We might say intuitively at this point that the OLS slope is equal to the sample covariance of x and y divided by the sample variance of the explanatory variable x. Now, as promised, it's quite easy to show that given the values of b1 and b2, the sum of the regression residuals must be equal to 0. We already know this from the OLS normal equations, but here's how we would do it mathematically. So in the first line on the column on the right, what I do, moving from the first line to the second line, is I break the parentheses. Then, if I insert the definition for the OLS slope, b sub 1, I now consolidate that on the right, and then on the left-hand side of the third line, I have all the remaining terms from the line preceding it, and you'll notice that each term also has its negative within the same line. So this expression is very clearly equal to 0, which we knew. We can also do this using matrix math. So to do this, what we first need to do is define the equation using matrix notation. So let us now define the vector y, which is a column vector of all the individual observations of y. We start with the first observation, y sub 1, all the way to the final observation, y sub n. Beta tilde is a vector of the linear parameters. It's the intercept, beta tilde 1, and the slope, beta tilde 2. X is a matrix of our explanatory variables. The first column is everywhere 1. The second column is the values of x, starting from the first observation, x sub 1, all the way through the final value, x sub n. And then likewise, E is a column vector of the OLS residuals. We can define the regression equation in matrix math now as y equals x beta tilde plus E. This is exactly equivalent to the definition we gave for the simple OLS equation in the scalar math section mere moments ago. The sum of the squared residuals is now defined as E transpose E. So if E is a column vector of the residuals, E transpose is a row vector of the residuals. And I show that in the final line. If I have a row vector of residuals multiplied by a column vector of residuals, you recall that when I do matrix multiplication, what I would do now is I would have E1 times E1 plus E2 times E2 plus E3 times E3 and so on and so forth up to E sub n times E sub n. And this expression is exactly equivalent to the expression I had in the scalar math section, which was the sum over observations I equal 1 to n of E sub I quantity squared. This is exactly equivalent but written in matrix math. Now, given the definition of the equation y equals x beta tilde plus epsilon and the definition that I have for the regression residuals from the previous slide, I can re-express the sum of the squared residuals in terms of y and x. So here I substitute in the definitions of E and E transpose and then multiply these terms. So as I move from the second line to the third line of the expression for the sum of the squared residuals, I have y transpose y transpose times x beta tilde, and then taking the second part, x beta tilde transpose it becomes, remember when you transpose a matrix or a matrix expression which has multiple terms, what you do is you invert the order of the terms and transpose each term individually. So the transpose of x beta tilde is equal to beta tilde transpose times x transpose. So I have that expression times y, and then beta tilde transpose x beta tilde. Now, because these terms are scalars, meaning they are 1 by 1 matrices, the two center terms, since it's one syllable rather than multiple, permit me to express this as y prime. So I have y prime x beta tilde and beta tilde prime x prime y are equivalent because the transpose of a scalar is equal to the scalar. So I can simplify it to this final term, and then to minimize this sum of the squared residuals, I need to perform matrix partial differentiation. And let me refer you to your favorite linear algebra text, or come by my office if you want. My favorite reference for just basic rules of matrix differentiation is Jan Kamena's text, Elements of Econometrics. It's a classic graduate school econometric theory text. So when I take the derivative with respect to beta tilde, I get this expression, 2 times x transpose y minus x transpose x beta tilde. And those must equal a column vector of zeros. So if I manipulate this then, what I have then is x prime x beta tilde must equal x prime y. And if I want to move x prime x from the left side of the equality to the right side of an equality, if these were scalars, what we would do is we would divide by x prime x. But since x prime x is a matrix, it's not a 1 by 1 scalar, the way I would move it to the right-hand side of the equality is by pre-multiplying by its inverse. Its inverse is x prime x quantity inverse. So if I multiply those, pre-multiply both sides of the equality with x prime x quantity inverse, I get the expression b, which is the OLS estimates, are equal to x prime x quantity inverse x prime y, which is the classic matrix definition of the OLS estimators. The reason why I have b on the left-hand side, of course, is that any matrix pre-multiplied by its inverse is the identity matrix I, and the identity matrix is the matrix equivalent of the scalar 1, right? So if I multiply any scalar expression by 1, I get the original expression back. In much the same manner, if I multiply any matrix expression by the identity matrix I of proper dimension, I get the original matrix back. So, to show that these two definitions, the matrix definition and the scalar definition, are mathematically equivalent, we must first consider matrix inversion. And we'll just do the very simple one. Since we have one explanatory variable, x prime x is a 2 by 2 matrix. And it turns out that a 2 by 2 matrix has a very well-known closed form inverse that you remember from linear algebra. So if I have this 2 by 2 matrix with elements A, B, C, and D, then the inverse is equal to 1 over AD minus BC, which is in matrix algebra called the determinant of the matrix. So 1 over the determinant times D minus B minus CA. Applying this now to our matrix of interest, x prime x, let me first remind you of what x prime x is. You remember x is the definition of x is repeated on the far right of the first line. It's a column of ones and then a column of the observations of x, x1 through xn. When I transpose that, remember what I do is the rows become columns. So, excuse me, the columns become rows. So the first row of x transpose is a row of ones. The second row of x1 is a row of the individual observations of x. If I do matrix multiplication, x transpose x, I get this expression on the second line. All right, so the upper right element, I have 1 times 1, and then I take the second element of the first row of x transpose, the 1 times another 1, and I'm adding 1 times 1 n times, right? So that's why that expression is equal to n. Then the first column times the first row times the second column gives me the value on the first row, second column of x prime x. So it's equal to the sum of the individual x's. This is a symmetric matrix, so the first element of the second row is the same as the second element of the first row. And then finally, in the final column and bottom row, we have the sum of the individual x's squared. So when I apply the formula for inverting this matrix to this particular example, I get x prime x quantity inverse is equal to 1 over n times the sum of the xi squared minus the sum of the individual x's quantity squared times this reordering of the elements. Okay. So the matrix estimator of the OLS equation B, which is x transpose or x prime x inverse x prime y, if we now state which each element is, we have a definition of x prime x quantity inverse from the previous slide. We know what x is, we know what y is. Now, as I multiply these elements out, let me multiply the final two elements together. Those are relatively straightforward. X times y. The first element is equal to the sum of the y's. The second row, that element, is equal to the sum of each individual x times each individual y. And then I'm repeating the formula we developed from the previous slide for x transpose x quantity inverse. Okay, now, if I go ahead and multiply these elements out, I get a rather scary looking expression for B1 and B2. These are not the expressions that you remember from your introductory scalar-based econometric theory course, but in the remainder of this lecture, I'm going to show you that these two are actually numerically equivalent. Okay. So to start with that, I'm going to tackle a couple individual pieces, and then we're going to combine them together and get the result of interest. So the first thing I can say is the sum of xi minus x bar quantity squared, which you remember was the denominator of the OLS slope. If I square each of those individual terms, I get the expression on the right-hand side of the equality on the first line. So I get the sum of each individual xi quantity squared minus 2x bar x sub I, and then plus x bar quantity squared. Now, if I break the parentheses and apply the summation to each term individually, I get the second line, right? So I'm summing the individual xi squared. And then because both 2 and x bar don't have a subscript I in them, they can be moved to the left-hand side of the summation notation. So I get this second term, minus 2x bar times the sum of the x sub i's. And then in a similar manner, what I'm doing is I'm adding, for the final term, I'm adding the constant x bar quantity squared n times. Now, what I can show here is that the sum of the x sub i's, you remember x bar, the sample mean, is equal to 1 over n times the sum of the individual x sub i's. If I manipulate that, what I get then is that the sum of the x sub i's is equal to n times x bar. So if I substitute that in, that's how I get from this second line to the third line. Right? That second expression of the second line is minus 2 times n x bar quantity squared. Okay? So if I take the denominator from the previous slide, and actually I have it repeated at the top of the second column. That was the kind of ugly looking denominator that we had for both B1 and B2. N times the sum of xi in the individual x sub I squared minus the sum of the xi's quantity squared. In the bottom of the first column, the first thing I'm going to do is I'm going to factor n out of that expression. So I can do that by factoring the n out of the first piece directly, but then if I factor n out of the second piece, because it didn't have an n to begin with, what I'm left with is 1 over n. So these two expressions are equivalent. Now, if I, on the second line of this current expression, I know that the sum of the x sub i's is equal to n times x bar for the same reason that I stated just moments ago. So n x bar quantity squared is going to equal n squared x bar squared. N squared x bar squared divided by n leaves me with n x bar squared. So because of this, what I can do then, moving to the second column, is the somewhat alien looking denominator for both B1 and B2. We can now transform it into something that looks more comforting and familiar. They're numerically equivalent. Now, to work on the numerator, we know that the numerator of the OLS slope is equal to the sum of xi minus x bar times yi minus y bar, or n times the sample covariance. So if I multiply out terms, I get the first thing on the right, and then breaking the parentheses, you see the pattern again. Now I break parentheses, and then what I do is I attempt to consolidate things in the middle. So so I know that the sum of the xi's is equal to n times x bar. I know that the sum of the yi's is equal to n times y bar. So putting both of those in, Now you see I can consolidate the final three terms into minus n times x bar y bar. Okay. And finally, I know this one seems a little bit odd, but I'm going to do it to match the numerators that we developed through matrix algebra. What I'm basically doing is I'm redefining x bar as 1 over n times the sum of xi, y bar as 1 over n times the sum of the yi's, and I get this final expression. So what I can say then, if I substitute this last result into the numerator of my B2 expression, I get the expression from the previous slide at the far right is now equal to the familiar result that we remember from the scalar math, right? The two n's cancel out, and I get the sample covariance upstairs between x and y, the sample variance of x downstairs. So this is the OLS slope. Now, to deal with the intercept, what we will do is I'm going to take x. So notice the second term of this expression, the sum of the xi's squared. I'm going to expand that into, on the right-hand side, into this expression that's enclosed by parentheses. The sum of the xi squared, I claim, is equivalent to the sum of xi minus x bar quantity squared plus n times x bar quantity squared. The reason why those are equivalent is I'm in essence adding and subtracting x bar, which of course is allowable, right? The reason why I'm going to do that is I am now going to move that last term, the n x bar squared, from the first additive expression to the second one, right? So I have now in the second line, I have the sum of y sub I times the sum of xi minus x bar quantity squared, and then I've shoved everything else to the right-hand side. This first expression, what you will notice is I have the sum of xi minus x bar quantity squared in both the numerator and the denominator. Those can be canceled out, and I'm left with the sum of yi minus the sample size n, and that's of course equal to y bar, the sample mean of the dependent variable. Then I have to manipulate this term that is on the right. We know, since we already know the answer, we know that this should equal b2 times, it should equal minus b2 times x bar. So manipulating this, I will first attempt to factor x bar out of this equation. So that's very easy to do, right? It's very easy to do on the first expression. The second one, the way I moved x bar out of that, you remember again that the sum of the xi's is equal to n times x bar. So that's how I factor that second expression out. And then moving, you see, I apply a result from a couple slides back. I can rearrange that expression now as the sum of xi, yi minus n x bar, y bar, right? And we're getting closer yet. Then from the previous slide, we showed how that expression was now equivalent to the definition of the OLS slope, B2. The n's cancel out, and I'm left with y bar minus x bar B2, which is the scalar math definition of the OLS intercept B1. So what we've done now is we've considered the ordinary least squares estimator as an algebraic tool and nothing else. We've derived it with scalar math, we've derived it with matrix math, and we've shown that the two are numerically equivalent.